This is a tutorial to perform a chi-squared goodness of fit test on discrete data. This example is going to be building off the existing example we developed for the Cafe Java coffee demand distributions. Previously we developed two process generators to generate samples from an observed distribution of none, small, medium, and large demands. The previous process generators were developed using the inverse transform method and the accept-reject method for producing samples from this particular distribution. The previous results show that the demands generated from these two methods seem to resemble those observed from our experimental evidence. However, we may want to run a goodness of fit test to statistically verify that these results do indeed follow the observed distribution. The statistical test for discrete data to perform goodness of fit is the chi-squared test. The test statistic is computed by comparing the observed frequencies for particular categories. So for example, the observed number of counts that were generated for the inverse transform method and the accept-reject method. Comparing those with those that would be expected from the underlying or proposed distribution. So previously we had calculated the probability mass function, or PMF, for the observed data. And to generate an expected number of demands, we simply have to multiply the PMF times the number of samples that we had generated. So this code for the PMF times the number of samples I'm going to store as the expected counts. So counts expected PMF times the number of samples. And actually to avoid the results changing every time I run the script, I'm also going to assign a random number seed at the top of the script. I'm going to say the numpy random seed is 0. So every time I run the script, I'll get the same exact results that are displayed here in the console. Okay. So now I have the counts that would be expected from our target PMF. And we next have to compute the chi-squared test statistic. So I'm going to store that in a variable t. So the chi-squared test statistic is found by taking the difference between your observed, or in this case generated counts, let's say from the inverse transform method, the difference between that and the counts that would be expected from your target distribution. That difference is squared and then divided by the counts from your target distribution. And finally, this is a statistic, or this is a equation that applies to each of the different levels, so none, small, medium, and large. And the overall chi-squared test statistic takes the sum of these across all of the values. So if I run this script, I have now computed my chi-squared test statistic, which I stored in the variable t. For this particular random number seed, it turns out to be about 0.32 or 0.33. And we're interested how this would compare to a critical chi-squared test statistic value that would lead us to reject the null hypothesis that there are no difference between the distributions from which these variables come from. So to compute a critical chi-squared test statistic, there is no equation or formula for it, and instead we'll have to use a statistics library. In this case, I'm going to import the scipy.stats library. I'm going to refer to it as stats as a shorthand. The stats library has in it many different distributions, and one in particular is the chi-squared or chi2 distribution. Many of these distributions have a property called the PPF. The PPF is almost like an inverse cumulative distribution function. It tells you what value of a random variable from this distribution is likely at a certain level of significance. So in our test, we may be interested in understanding what is the 95th percentile chi-squared test statistic. And in this case, we also need to identify what are the degrees of freedom to pass to the PPF. Remember that the degrees of freedom for a discrete variable is the number of options that there are minus 1. So in this case, there are 4 different levels of demand. So we have 4 minus 1, or 3 degrees of freedom. Now, the result of this function call I'm going to store in a chi underscore crit variable. And just to run this for you, I'm going to look in the console to see what the chi crit variable is. So in this case, it appears that if our test statistic is anything above 7.81, it would mean that with 95% confidence, we could reject our null hypothesis and infer that the distributions come from the samples come from 2 different distributions. In our case, though, our t-value was only 0.32 or 0.33, which is much less than this critical value, leading us to the realization, or leading us to not be able to reject the null hypothesis, and inferring that our data do indeed come from the same distribution in this case. Now, we computed this chi-squared test statistic by hand, but you can also compute it with a statistics function. And this is often much more useful because it will return also the p-value or the significance value of your statistical test. So in our case, we can run using the stats package. There's a separate function called stats.chi-square in words, which runs a full chi-squared goodness of fit test. The arguments of this function, if we look at it in the object inspector, it requires an array of the observed frequencies in each category, and then an array of the expected frequencies in each category, and any changes to the degrees of freedom that it would otherwise compute by the length of this array minus 1. And what it returns is the value of the chi-squared test statistic, which we previously called t, and also the p-value or the significance of the test. That tells us what level of critical value could we go up to and still have significant results. So in our case, let's give this chi-squared test function the 2 arguments, the number of counts that we observed in the IVT test, for example, the IVT process generator, and the counts that we would expect. And in this case, we don't have any delta degree of freedom, so we actually don't need a 3rd argument. And the results of this function we can store in 2 new variables. I'm going to reuse the variable t and also introduce the variable p to store the results of the significance. So let's run this test. We can see the t-value that's now computed from this chi-squared test is exactly the same as we had manually computed before, 0.32 or 0.33. And our p-value is very high. A high p-value means that it's very unlikely that our null hypothesis could be rejected. So together, these results give us a high degree of confidence that our data do indeed come from the same distribution. Now, the important factor for running statistical tests, including the chi-squared goodness of fit test, is identifying a good level of significance, which again previously we had chose 95%, which is also the level of 1 minus p that we accept. So in this case, for the random number seed of 0, it looks like our result did follow expectations. However, if I remove this random number seed and run the statistical test again, look at the p-value. In this case, it was still quite high, 0.82, which means that our data likely follows the same distribution as expected. But if we run this multiple times, at some point, it's actually very likely that we would see a low p-value. So this time it was 0.24. This next time it's 0.72. Next time it's 0.03. So traditionally, if you saw a p-value of 0.03, You would reject the null hypothesis at, say, a 95% confidence level and say that these data come from different distributions. However, we know in this case that they really don't. The data are drawn from essentially the same distribution, and it's just random chance that they happen to be different. The important part about these goodness of fit tests and statistical tests in general is that they're only as good as the level of confidence.